Here are the answers to Unit 7 for your response question B. Unit 7 covers differential equations. Please have your workout as you're looking at this video so you can check to see your answers against the correct solutions. So the first part talks about liquid fertilizer being put into a hydroponics growing system, and the amount of fertilizer F satisfies the logistic differential equation given right here. This means that the rate that the fertilizer is being put in depends on the amount of fertilizer. You're supposed to find the limit for the amount of fertilizer as t approaches infinity and the limit for the rate of the fertilizer being added as t approaches infinity. So what you need to recognize is that a logistic differential equation written this way doesn't quite match the form. Have this form on your formula sheet and say to yourself that probably converting this given one into this form would be beneficial. So if we take this 6 and factor it out, the first term is a 1, which is the way that the differential equation should have. And you wind up with 2f, 1 minus f over 6. 2 is the k, or the constant. More importantly, L, the carrying capacity, is 6. That means that as time goes on, the amount of fertilizer approaches the carrying capacity of 6. And then for all logistic differential equations, the limit as time goes on of the rate is 0. Logistics look like this. So as you get closer and closer and closer to a very large time, the rate, their slope becomes 0. What's different about this problem is that at time equals 0, we don't start at a very small amount. We start at the halfway point of 3, and that'll become important in the next question. Part B says find the value for the rate at time when f is increasing most rapidly. Give a reason. So the greatest rate occurs when the output, or the y value, is half of the carrying capacity. And in the first graph, this first solution, I showed you that if the carrying capacity is 6, then the greatest rate occurs when the y value is 3. Plugging that value into the differential equation produces the rate is 3 when the fertilizer is 3. Part C asks you to find the second derivative in terms of f. And the biggest issue with this question was not recognizing that we had implicit differentiation. If you want the second derivative for the amount of fertilizer with respect to time, after you take the derivative of f, you need to include a df dt. Instead of using the product rule, I distributed the 1/3 f and produced a polynomial, and then I can just do term by term derivatives. So the derivative of 2f is 2 times 1 times df dt, and the derivative of this term is negative 2/3 f df dt. If you factor out the df dt, you wind up with df dt substituted is what you were given originally, 2f minus 1/3 f squared. Doing a little bit of simplifying, there were lots of different but correct answers. You didn't have to have yours look like this, but something along the lines of any of these is correct. And then finally, you were asked to do two things in Part D. Use Euler's method to make a prediction at time t equals 1 month, and then state whether your approximation is an overestimate or an underestimate. Euler's method are very common questions on an AP test, and they'll give you part credit as long as you set up your Euler's method correctly. So set up a table, start with an ordered pair, calculate the slope at a certain point, and then calculate the new y value by saying, take the old y value, add on the slope times the time increment or the delta x increment, and that becomes your new y value. So starting here, the slope at that point is 3. Substituting that into this formula produces 4.5. So after half a second, we have 4.5 fertilizer. Calculate the slope again. Calculate your new y, and your final output is here. This was supposed to be a no calculator question, so make sure that you can do this either with fractions or with decimals. And then answer the second part, is it an overestimate or an underestimate? At 1, if we looked at the plot from the original first screen, at 1 we are past the halfway point in terms of the approaching the carrying capacity. So the slope or the curve is concave down, which means tangent lines would be above concave down functions, or the approximation, which is coming from a tangent line, is going to overestimate the actual value.